Hello and welcome to the Easy Sleep Science Channel. Tonight we'll turn our attention to the quiet green companions who share this world with us. Trees stand still, rooted deep in the earth, seemingly motionless, yet their lives are full of hidden stories and extraordinary abilities. They can talk to one another, defend themselves with strange tricks, and even emit sounds that humans are only beginning to understand. And they breathe life into this planet. Among them we find both wonder and peace. Most of the time we barely notice. We walk past trees, fields, and flowers as if they were just a backdrop decorations for the busy world of animals and people. But plants are far from passive. They sense light and gravity, keep track of time, share resources through underground networks, and even hold memories of stress and change. Science is only beginning to uncover the world of plants, and it's far more complex than we ever imagined. As always, if you enjoy drifting off to gentle stories of science and wonder, please like, subscribe, or share your thoughts below. Now, let the noise of the day fade away. Relax, breathe deeply, and let your mind wander through the mysterious world of plants. Let's begin. Some plants can communicate through chemical signals. Though they cannot speak, they have their own language. When an insect chews a leaf, the plant releases chemical signals into the air compounds that drift toward neighboring plants to warn them of danger. When nearby plants smell this warning, they respond by producing bitter or toxic compounds that make their leaves harder to eat. It's as if an invisible network of messages is constantly passing across meadows and forests. This ability isn't limited to one species. A single attacked plant can send signals that other trees, shrubs, and even grasses understand. To us, a green field might look silent, but for plants, it's alive with conversation. They aren't solitary beings. They're members of a collective defense system, an ongoing chemical dialogue happening all around us. Plants also share nutrients through vast underground fungal networks. Beneath the soil, roots connect with fungi in huge systems called mycorrhizal networks. Through them, plants exchange sugars, minerals, and chemical signals. A large, healthy tree can send extra carbon to young saplings struggling in the shade. A sick or damaged tree might receive nutrients from stronger neighbors. In some forests, scientists have found that trees even favor their kin, sending more resources to their offspring than to unrelated trees. This system is called the Wood Wide Web, an underground network that allows the whole forest to act like a single living organism. Above ground, each tree seems to stand alone, but below they're bound together in a constant exchange of life. Whenever you walk through a forest, remember, beneath your feet, thousands of invisible threads are weaving a community. Some flowers can generate their own heat. Beyond opening their petals, certain species can actually warm themselves a few degrees above the air around them. The skunk cabbage, for example, melts early spring snow, with its own warmth attracting pollinators even in the cold. This heat not only lures insects, but also helps the flower's scent travel farther. Other species, like the giant water lily, stay warm through the night, providing a cozy refuge for beetles. This biological trick costs energy, but it pays off in higher chances of reproduction. A fragile-looking blossom can, in truth, be a tiny furnace glowing quietly in the dark. Roots can use a kind of sonar to find their way underground. In darkness, roots search for water and nutrients, avoiding obstacles as they go a journey that seems blind but isn't. Roots emit faint rhythmic clicks too soft for human ears. Scientists believe they may sense the echoes of these clicks, a primitive form of sonar. By hearing their own echoes, roots can navigate the complex underground world. They even tend to grow towards specific sound frequencies, a mysterious sense of hearing we still don't fully understand. Beneath every tree and flower bed, a silent world is listening, feeling its way forward through sound. Some seeds can sleep for thousands of years and still sprout. Seeds are nature's time capsules. Most germinate within weeks or months, but some wait hundreds, even thousands of years. Scientists once revived a lotus seed buried for over a millennium. It grew into a healthy plant. Another Arctic flower was brought back to life from seeds frozen in permafrost for tens of thousands of years. Seeds endure by entering total dormancy, suspending nearly all biological activity until the right conditions arrive. A tiny seed may be older than civilization itself, yet still holds the spark of life waiting for its moment to awaken. The corpse flower attracts insects with the smell of rotting flesh. Known as Titan arum, it boasts one of the largest blooms on Earth and one of the foulest odors. When it blooms, it releases a stench like decaying meat, revolting to humans, irresistible to flies and beetles that feed on carrion. The flower also warms itself to spread the scent, mimicking the heat of an animal carcass. Each bloom lasts only a few days and draws crowds of visitors who come to witness and endure the smell. But for the plant, it's pure strategy. By imitating death, it ensures life. Some plants can clone themselves for tens of thousands of years. Many of Earth's oldest living beings are not single trees, but vast colonies of genetic copies. In North America, trembling aspen forests spread by sending up shoots from a shared root system. Each stem may live a few centuries, but the common root network can persist for tens of millennia. One famous colony in Utah, called Pando, spans more than 100 acres and is estimated to be at least 80,000 years old. From above, it looks like a normal forest, but in truth, it's one single organism, one body, stretching through time. Plants can hear the sound of insects chewing on them. Though they lack ears, they can still detect vibrations. When caterpillars gnaw on leaves, the vibrations are picked up by the plant. Immediately, it produces defensive chemicals that make its leaves less palatable. Amazingly, plants react only to the specific vibrations of being eaten, not to harmless movements like wind. That means they have a subtle awareness of their environment, sensing danger through vibration instead of sight or sound. Imagine a leaf recognizing the sound of its own damage and responding in an instant. It's a soundscape of life without ears, guided purely by touch. When under stress, plants also make mysterious clicking sounds that we can't hear. Using ultrasensitive microphones, scientists have recorded ultrasonic pops from dehydrated or damaged plants, such as tomatoes and tobacco. These sounds are inaudible to us, but clearly visible on instruments. The cause is still debated. It might be tiny air bubbles bursting in the plant's water channels, or perhaps a form of distress signal. Either way, the discovery changes how we think about plants. They are not silent at all. They may cry out in thirst, their invisible music of stress echoing through the green world. Some desert plants drink water from fog. In places where rain is scarce, life must get creative. Certain species evolved special leaves or spines that pull moisture straight from the air. Microscopic droplets flow down the plant and reach the roots, a lifeline when the soil is bone dry. The Namib desert beetle's favorite plant, for instance, uses fine hairs to draw water from drifting fog. Cacti and succulents do the same, turning vapor into survival. To us, the desert may seem lifeless. To plants, it's a place to drink from the air itself. Forests can make rain. They don't just catch rainfall, they help create it. Through transpiration, trees release water vapor into the air, which rises, condenses into clouds, and returns as rain. In dense places like the Amazon, this effect is so powerful that forests generate their own weather systems. Some scientists believe that if forests vanish, the rain will too, turning fertile lands into dry plains. So when you stand under a canopy, remember, it's not just shade above you, but a living fountain feeding the sky. Some orchids trick insects with the scent of a female bee. They release chemicals that mimic female pheromones, luring in eager male bees who attempt to mate with the flower. In the process, pollen sticks to their bodies and gets carried away, completing pollination perfectly. The deception is so precise that even experienced bees fall for it. Some orchids even shape their petals to resemble the body of a female insect, a clever illusion that lets them reproduce without offering any nectar at all. And finally, the largest living organism on Earth isn't a tree or an animal, but a fungus that connects with forests. In Oregon's Blue Mountains, a massive fungus spreads nearly 10 square kilometers underground, intertwined with countless tree roots. Above ground, we see only small mushrooms, but beneath lies a single organism weighing hundreds of tons and thousands of years old. It reminds us that life doesn't always reveal itself on the surface. Something small may in truth be enormous, hidden below, sustaining the forest itself. And when the sun rises, sunflowers turn their faces toward the light from east to west, then back again to greet the dawn. They track the sun to capture as much light as possible. When mature, they face east, catching the morning warmth that attracts pollinators. It's a quiet dance of life, steady, graceful, and full of wonder. Many other plants move too, turning leaves and blossoms to follow light throughout the day. This daily rhythm, almost invisible to us, becomes a graceful ballet when seen in time-lapse, a slow choreography led by the sun. What seems still is in fact a never-ending dance guided by light. On land, plants in some regions produce more oxygen than all the ocean's algae combined. We often hear that marine plankton create most of Earth's oxygen. And that's true globally, but in certain areas, terrestrial plants are the dominant breathers. In the Amazon basin, for instance, dense vegetation makes it one of the planet's greatest oxygen factories. This green lung recycles carbon dioxide into fresh air, nourishing not just local ecosystems, but the whole world. Even though the oceans are vast, land plants can concentrate productivity in remarkable ways. Each tree and blade of grass contributes to this quiet abundance, creating the very air we depend on. It's humbling to think that the breath you just took may have been shaped by forests thousands of miles away. Some plants can survive being completely frozen. In Earth's harshest places, life endures what should be impossible. Arctic mosses and alpine species can survive months encased in ice. Their cells produce protective proteins and sugars that prevent deadly ice crystals from forming inside. When the thaw comes, they revive almost instantly, resuming growth as if nothing happened. Some endure repeated freeze-thaw cycles unharmed. This adaptation is not only a marvel of nature, but a scientific treasure offering insights for preserving crops or even human tissue. Fragile as they seem, these survivors are among the toughest on Earth, thriving where temperatures plunge far below freezing. That resilience reminds us that life can persist in places we once thought uninhabitable. Cacti, for example, can live for centuries with barely any water, masters of endurance in arid lands. With thick, waxy skins and water-storing tissues, many survive months, even years without rain. Some giants, like the saguaro, can live for more than 200 years, weathering endless cycles of drought and flood. Their spines cast shade and reduce water loss, while shallow roots spread wide to gather even the smallest drops. Inside, they store gallons of water in expandable tissues, turning themselves into living reservoirs. That endurance makes cacti the icons of the desert, symbols of patience and perseverance. To walk among them is to meet a community of silent giants who have mastered the art of waiting. Long after other plants fade, they endure, guarding their hidden wells of life in perfect stillness. Some plants glow faintly at night under the right conditions. Bioluminescence is rare in plants, but now and then a soft radiance appears in special circumstances. Some fungi that live with trees shine, laying eerie green streaks across the forest floor. Recently, scientists have even engineered glowing plants by inserting genes from bioluminescent organisms. These luminous plants aren't just magical to look at. One day, they might become natural light sources and reduce electricity use. Even without genetic modification, certain plant tissues fluoresce under ultraviolet light, revealing hidden patterns invisible to the naked eye. Imagine walking through a forest where leaves emit a ghostly glow like living lanterns. Though naturally glowing plants are very rare, the phenomenon reminds us that life can bend the rules of chemistry to create beauty in unexpected ways, and what seems ordinary by day may hide a faint shimmer in the dark. Lotus seeds can germinate after more than 1,000 years. The sacred lotus isn't only a symbol of purity and rebirth, it also bears some of the longest-lived seeds known to science. In one case, a lotus seed found in the bed of a dried lake in China was dated to over 1,000 years old, and when planted it sprouted into a healthy plant, as if it had only slept through a single season. This extraordinary longevity is thanks to a tough protective coat and the seed's ability to almost shut down its metabolism like freezing life. A pause button on existence. Buried and forgotten for centuries, the seed still holds a spark, and every lotus that blooms from such ancient beginnings carries not only beauty, but a story of endurance across time. Some trees can remember drought and adjust their growth accordingly. Trees keep a journal of their lives in their rings. In dry years, they form narrower rings that record harsh stretches of time. But beyond recording the past, some trees seem to adjust future growth based on prior stress. After a drought, they often grow more cautiously, conserving resources as if bracing for drought's return. This memory is written into their physiology, changing how they manage water and energy, an astonishing adaptation that blurs the line between memory and instinct. A tree that has endured hardship does not forget it carries the lesson forward, shaping its survival strategy. In that way, trees are resilient, not only in the present, but across decades, even centuries. Every trunk in the forest contains not just wood and bark, but a history of struggle, adaptation, and quiet memory. Plants release chemicals when attacked to warn their neighbors. When insects chew leaves, the damage doesn't go unnoticed. Many species respond by emitting volatile compounds into the air, invisible smoke signals that drift to nearby plants. Once the neighbors detect the alarm, they activate their own defenses, producing bitter, or toxic compounds to deter leaf eaters before the attack arrives. Some studies even show plants can distinguish different threats, releasing one signal set for leaf-chewing caterpillars and another for aphids. In a sense, plants broadcast distress into the air, forming an invisible communication network that helps whole communities survive to us. The air seems empty, but in reality, it's crowded with chemical conversations, a quiet code of warning and defense that shapes the fate of fields and old-growth forests. Some plants launch their seeds like tiny rockets. Not every plant relies on animals or wind. Some shoot seeds with explosive force. The tukmano tree, for instance, develops fruits whose tightly coiled seeds spring open when dry. A light touch triggers a snap that flings seeds several meters. Others, like the squirting cucumber, pump pressure into the fruit until it bursts, spraying seeds in a liquid shower. This ballistic dispersal looks small but works brilliantly. By blasting seeds far away, plants reduce competition with their own offspring for space and resources. Witnessing one of these micro-explosions reminds us that even in the quiet plant world, bursts of energy and sudden motion can happen. Each launch is a tiny drama hidden inside an ordinary fruit until the moment it pops. Mangroves can filter salt from seawater. They thrive along coasts where most trees would quickly die. Living in brackish, salty water while keeping their inner tissues fresh, mangroves possess remarkable adaptations. Some filter salt right at the roots, letting only fresh water pass into their vessels. Others shunt salt into older leaves that later drop off. Still others excrete salt through tiny pores on the leaf, leaving visible crystals behind. Thanks to this, they build vast tropical coastal forests that provide essential habitat for fish, birds, and countless other species. To us, seawater seems unlivable for trees, but mangroves have made it home, standing like living coastal sentinels. They defy salt with sophisticated biological tricks, showing how resilience can turn a harsh edge of the world into a thriving ecosystem. Some carnivorous plants create traps filled with digestive juices. Carnivorous plants evolved to supplement nutrients by consuming insects, even small animals. The most striking example is the pitcher plant. Its leaves roll into deep, slippery tubes filled with digestive fluid, and the rim is often slick or lined with downward-pointing hairs, making escape nearly impossible once prey slips inside. Drawn by bright colors or nectar, the victim falls in and drowns, then slowly breaks down. The plant absorbs the nutrients, gaining an edge in nutrient-poor soils where other species struggle. In some tropical species, the pitchers grow large enough to catch frogs, lizards, or even small rodents, blurring the line between passive greenery and active predator, reminding us that survival in nature can take forms beyond imagination. The Amazon rainforest produces about 20% of the world's oxygen. The Amazon is called the lungs of the earth because its vast vegetation exhales immense amounts of oxygen through photosynthesis, estimated at roughly 1/5 of the planet's supply. Every old-growth giant and every understory layer contributes to that global cycle, turning carbon dioxide into fresh air that sustains life. Beyond oxygen, the Amazon regulates climate, stores colossal amounts of carbon, and recycles rainfall. Yet its forests are fragile. Deforestation and climate change threaten to upset these delicate balances, with consequences far beyond South America. When we speak of the Amazon, we're not just talking about a place, we're talking about a planetary system, a mechanism that breathes life into the world, and walking its shaded paths is stepping inside the very engine of Earth's atmosphere. The same plant species can taste different, depending on the soil it grows in. The flavor of many plants is shaped not only by genetics, but by the ground beneath them. Grapes grown in different regions, for example, develop distinct flavors based on soil minerals, microbes, and moisture. The concept of terroir in winemaking explains why the same grape variety can yield very different wines depending on where it's grown. Herbs like basil, mint, and rosemary also shift their aromas with soil conditions. Even vegetables like carrots and potatoes mirror the chemistry of their environment. What appears to be a single species is in fact a multitude of subtle variants, each molded by the landscape. Every bite carries the signature of the earth it grew in, a reminder that plants don't just live, they are bound to the soil and ecosystems that nourish them. Leaves can change color not only in autumn, but also in response to stress. We often link vivid foliage to the fall season, but pigments can shift for other reasons. During drought, nutrient shortage, or injury, some species alter their leaf chemistry. Green chlorophyll may fade, revealing the yellows, oranges, and reds beneath. In other cases, the plant actively produces protective pigments called anthocyanins to shield tissues from sunlight or deter herbivores. These stress-driven color changes can make a plant look like it's in early autumn in the middle of summer, beautiful to us, but often a sign of struggle. The shifting palette shows that plants constantly respond to their environment, adjusting not only growth, but also chemistry and appearance. A sudden splash of color in a green field may be less a seasonal marker than a signal of hidden challenges the plant is facing. The tallest trees rise higher than a 30-story building. In California's fog-shrouded forests, coast redwoods reach dizzying heights. The tallest known tree, nicknamed Hyperion, stands over 380 feet taller than a 30-story building. These giants are so tall that their top canopies live under entirely different conditions than their bases: thinner air, brighter light, and stronger winds. Water must be pulled up through a trunk wider than a city street, a bioengineering feat pushed to the limits of plant physiology. Despite their vast size, they spring from seeds no larger than a tomato seed. Their existence reminds us that tiny beginnings can reach extraordinary heights. Standing beneath a redwood, staring up until the crown vanishes into mist, feels like gazing at a living skyscraper, not built of steel, but of centuries of patient growth. Some flowers bloom only at night to attract moths. Not every blossom seeks daylight. Some save their beauty for darkness, opening when night falls and the stars appear. These night flowers often release strong fragrances that travel far in still air, enticing moths and other nocturnal pollinators. Species like moonflower and evening primrose open at dusk, forming pale silhouettes that glow faintly under the moon. This strategy reduces competition with daytime flowers and taps into partners who work the night shift. To us, a flower unfolding under starlight is pure magic. To the plant, it's practical survival, a reminder that life's rhythms are wonderfully diverse. While some bask in the sun, others reserve their brilliance for the quiet hours when the world sleeps. Trees can grow roots that rise above the ground to breathe in swampy soil. In waterlogged, muddy habitats where oxygen is scarce, many species develop special aerial roots that reach above the surface. Mangroves, for example, produce snorkel-like structures called pneumatophores, allowing them to draw oxygen directly from the air. Bald cypress trees form knobby knees around their trunks that protrude from the water with a similar function. These adaptations let trees thrive where most species would suffocate, a reminder that life will reshape even its most basic structures to meet environmental challenges. Some seeds hitchhike on animal fur to get around. Seeds have evolved countless tricks for travel, and one of the most effective is catching a ride. Many species grow seeds with hooks, barbs, or sticky hairs that cling to passing animals. When a deer brushes a meadow or a fox slips through a thicket, the seeds latch on and are carried miles before dropping into new ground. Humans aren't immune either. The burrs that snag your clothes are doing the same thing. This strategy lets offspring disperse well beyond the parent's canopy, boosting survival in new habitats. In fact, Velcro was inspired by the microscopic structure of burr seeds. The annoying tag on your socks is really an evolutionary masterpiece that lets plants cross landscapes without moving themselves. Some seeds can drift across oceans and still sprout. Certain species don't send seeds with beasts or breezes, but with waves. Coconuts, for instance, produce buoyant, water-resistant seeds. They can float thousands of miles across salty seas, wash ashore on distant beaches, and take root. Other species, from mangroves to some legumes, also have natural floats, little rafts built for long sea voyages. Ocean currents become invisible highways for seeds, ferrying capsules of life between continents. Every coconut that germinates on a sandy shore is proof of a remarkable crossing, a seed that sailed an ocean carrying the blueprint for a tree inside its sealed shell. Some plants fold their leaves when touched. Few react to contact as dramatically as the sensitive plant Mimosa pudica. When lightly touched, its leaves fold almost instantly and droop. A few minutes later, they reopen. This movement thigmonesty may startle herbivores or reduce further damage. Other species are touch-sensitive too, though slower adjusting leaf position when bumped. The mechanism relies on rapid changes in water pressure within specialized cells, tiny hydraulic systems at work. Watching a plant respond so quickly, as if aware of your presence, challenges the idea that plants are unfeeling. Even if we don't know exactly what a plant experiences, this sensitivity reveals a surprising layer of awareness in the quiet life of green. Plants can count the trap of the pitcher plant needs 2 touches to close. The pitcher plant Venus flytrap is an evolutionary wonder. The inner surface of the trap has sensory hairs that are extremely sensitive to movement, but the trap won't close after just 1 touch. It waits for 2 touches within about 20 seconds before snapping shut, avoiding wasting energy on raindrops or debris. Once the trap closes, subsequent touches trigger digestive enzymes that begin breaking down the prey. The Venus flytrap isn't merely a mechanical reflex. It processes information and makes decisions based on incoming data. This tiny predator blurs the line between plant and animal behavior, reminding us that intelligence in nature takes many forms, some hidden in the Carolinas marshes. Ancient ferns once dominated Earth before flowers appeared. Long before blossoms colored the landscape, ferns ruled the planet. In the Carboniferous period, hundreds of millions of years ago, giant tree ferns and their relatives blanketed vast swamp forests, helping shape the atmosphere by drawing down immense amounts of CO2, forming the coal seams we still mine today. With their elegantly coiled fronds, ferns spread across the globe in warm, humid climates. To this day, they remain highly successful, with thousands of species adapted to rainforests, deserts, and even cracks in sidewalks. Each time you look at a fern frond, you're seeing a survivor, a lineage older than flowers, fruits, and most of the modern plant kingdom. Pine cones open and close with humidity. Seemingly inert, a pine cone is a finely tuned moisture sensor. When dry, its scales open to release seeds. When damp, they clamp shut to protect seeds from mold. This movement needs neither muscle nor nerves, but arises from the cone's tissue structure, which swells and shrinks differently as it absorbs water. Some cones are sensitive enough to open and close repeatedly as the weather changes. For the tree, this ensures seeds are released only when conditions are favorable. To us, a cone may look like forest decor, but each one is a silent barometer responding to the environment. Place one indoors, and you can watch it open and close with changes in the air, a natural instrument born for survival. Some trees bleed red sap. Certain trees hide a surprise beneath their bark, bright red sap that looks like blood. The dragon's blood tree in the Socotra archipelago and Australia's bloodwood both exude red resin when cut or injured. For centuries, this resin has been used as a dye medicine and in rituals, prized for its strangeness as well as its uses. Seeing a tree bleed crimson can be startling, as if the plant world were mimicking the animal world. But this vivid resin is simply a defense sealing wounds and repelling insects or microbes. Even so, the uncanny resemblance lends them an aura of myth and mystery. Bananas are berries botanically, while strawberries are not. Botanical definitions don't always match everyday intuition. A true berry develops from a single ovary and has seeds embedded in the flesh. By that rule, bananas are berries, and strawberries are not strawberries developed from many ovaries in one flower, making them aggregate fruits. Tomatoes, kiwi fruit, and even grapes are berries in the botanical sense, though we don't always think of them that way. These classification paradoxes show how plants often defy our expectations. What matters isn't appearance, but structure and development. Next time you peel a banana, you're holding a bona fide berry. The strawberries in your bowl belong to a different category altogether, name notwithstanding. Some plants release caffeine to block rivals. Caffeine doesn't just wake people up, it's also a chemical weapon in nature. Some species, including coffee and cacao, release caffeine into the soil via fallen leaves or roots, making it harder for other plants to germinate nearby, and reducing competition for resources, a process called allelopathy that gives caffeine-producing plants more space and nutrients. At the same time, caffeine can act on insects as a mild pesticide, disrupting their nervous systems. For plants, there's no latte involved. It's survival using chemistry to tip the scales in a crowded ecosystem. Bamboo can grow nearly a meter in a single day. Bamboo holds the record as one of the fastest-growing plants on Earth under ideal conditions. Some species can stretch close to a meter within 24 hours. This astonishing speed comes from specialized tissues that elongate rapidly rather than building new cells one by one, letting bamboo shoot up seemingly overnight. In many places, bamboo provides essential materials for construction tools and even food. Its growth rate makes it a renewable resource that recovers quickly after harvest. Though it looks like a tree, bamboo is actually a giant grass. Its relentless surge a testament to the plant kingdom's adaptive power. Some desert wildflowers bloom only once in a decade. In the harshest deserts, a few species choose extreme patience, lying hidden as seeds for years, waiting for the rare combination of heavy rain and favorable conditions. When the moment comes, they erupt into spectacular carpets of color, covering places that are usually barren. In Chile's Atacama Desert, This is called the flowering desert, when a rare bloom transforms the sands into a living mosaic. These brief displays last a few weeks before fading back into dormancy. For the plants, this strategy ensures survival by hoarding energy for the most certain opportunities. For the lucky humans who witness it, the sight is unforgettable. A reminder that even where life seems absent, beauty and resilience linger beneath the surface, waiting for the right moment to rise. Plants can recognize relatives and grow differently when next to kin. Research shows some species can tell kin from strangers. Certain wildflowers grow taller and more competitive among unrelated neighbors, but become less aggressive among siblings. They can adjust roots, foliage, or chemical defenses depending on who's nearby. This kin recognition hints at a level of awareness we rarely attribute to plants. It helps family groups avoid draining shared resources while still outcompeting outsiders. The mechanisms are still being unraveled via chemical signals in the soil, subtle cues from reflected light, or other hidden processes. But the result is clear: plants possess remarkable discriminatory abilities, treating kin and strangers differently. Some trees are fire-adapted and sprout back from ash. For many species, fire isn't an endpoint, but the start of renewal. Eucalyptus, sequoias, and some oaks evolved thick bark that shields living tissues from flames. Others keep dormant buds under the bark or deep in the roots, ready to burst after fire passes. Some even require fire's heat to trigger germination, the heat-cracking seed coats. Far from being purely destructive, fire can clear competition, recycle nutrients, and open space for growth. Walking through a scorched forest and seeing green shoots emerge from blackened trunks is to witness resilience written in the language of fire. These trees don't just survive destruction. They use it, weaving flames into their life cycle and showing that even in ruin, renewal is possible. Some roots grow upward to seek oxygen in waterlogged soils. In swampy or flooded environments where oxygen is scarce underground, certain species develop specialized roots that grow upward instead of downward breathing roots. These aerial roots protrude from the soil like snorkels, allowing trees to absorb oxygen directly from the air. In North America, bald cypress produces characteristic knees around the trunk, believed to serve a similar function. What looks like a jumble of twisted wood on display is really an elegant solution to a hidden problem. Finding breath in a water-soaked world, a reminder that survival sometimes depends on reimagining even the most basic rules of growth. Leaves have tiny pores that inhale carbon dioxide. A leaf's surface may seem smooth, but under a microscope, it's dotted with countless stomata, tiny doors that open and close to let CO2 in for photosynthesis while releasing oxygen and water vapor, helping regulate a plant's temperature and humidity. The movement of these pores is finely tuned, responding to light, moisture, and internal chemical signals. Without stomata, plants couldn't absorb carbon or release the oxygen we depend on. It's astonishing that Earth's atmospheric balance rests on these minute openings, too small to see, yet so numerous they cover the planet like a living skin of breath. Pollination isn't always gentle. In some species, pollen is launched in sudden bursts, shooting straight onto visiting insects. Orchids, for instance, use spring-loaded mechanisms to latch pollen packets onto pollinators. Other plants build up tension in the anthers until a light touch blasts out a cloud of pollen. This explosive strategy ensures efficient transfer, fastening pollen to the visitor before it can escape. For a bee or a moth, it can be a jump scare. The flower sits still one moment, then fires its payload the next. For the plant, it's reproductive optimization. Beneath the calm surface, every blossom hides a mechanism brimming with energy, waiting for the perfect moment to release. Even in silence, flowers are engineers of movement, timing, and precision. Orchids also produce the smallest seeds in the world, dust-like. Their seeds are so tiny and light that they're almost invisible to the naked eye. Unlike most seeds, orchid seeds carry virtually no stored nutrition and instead rely on symbiotic fungi in the soil to fuel germination. Thanks to this relationship, orchids can produce thousands, even millions of seeds at once, sending them on the wind to colonize environments far from the parent plant. A dust-sized orchid seed still holds the potential for one of Earth's most intricate flowers. This strategy, making vast numbers of minuscule seeds, leaving much to chance, and depending on fungi, shows nature's willingness to experiment with extremes. Some trees keep their leaves year-round by making anti-freeze proteins. In cold climates, most plants shed their leaves for winter, but conifers like pines and spruces take another path. They produce specialized proteins that act like anti-freeze, preventing ice crystals from forming inside cells. Combined with waxy coatings and needle-like leaves that reduce water loss. These adaptations let conifers remain green in snow and photosynthesize whenever conditions allow, even in the coldest months. To us, dark green needles against white snow evoke permanence, a symbol of endurance. Behind that image lies chemistry, honed over millennia, allowing life to resist freezing cold. Every evergreen forest is living proof that plants can bend survival's rules, holding on to leaves long after others have fallen. Plants invented photosynthesis more than 2 billion years ago. The process that sustains nearly all life on Earth, photosynthesis, was pioneered by ancient plants and their microbial ancestors. By capturing sunlight to turn CO2 and water into sugars, these organisms transformed the planet. The oxygen they released accumulated in the atmosphere, paving the way for animal life. Before photosynthesis, Earth's skies held almost no oxygen. Afterward, everything changed forever. Every breath we take traces back to that ancient revolution. Today, photosynthesis still hums quietly in leaves, algae, and cyanobacteria all around us, maintaining our air and energy balance. It's easy to overlook a patch of green, but within it lies the same process that reshaped the world. Plants don't just adapt to their environment, they remake it, creating the conditions that make life as we know it possible. The Amazon breathes fragrant chemical clouds. In the rainforest, countless trees release volatile organic compounds into the air to deter herbivores, attract pollinators, or shield leaves from heat and light. At high concentrations, they create the forest's characteristic scent, a complex blend drifting above the canopy. But these emissions do more than perfume the air. They interact with atmospheric particles, influencing cloud formation and even rainfall. In other words, the Amazon doesn't just breathe oxygen, it seasons and helps reshape the air above it. Standing within such a forest surrounded by invisible plumes, we realize how profoundly plants shape their environment. They are not passive residents of Earth, but active engineers of air, water, and climate makers of the invisible cloud rising from leaves like breath. Some vines climb by feeling nearby surfaces. Living for light but unable to stand upright on their own, many species seek anchors. They extend tendrils, slender structures that sway until they touch something solid. On contact cells on the touch side slow their growth, while those on the opposite side elongate, causing the tendril to coil tightly around the support. Thus the vine latches on and slowly climbs toward the canopy. Some species can even distinguish rough from smooth surfaces, preferring textures that offer a better grip. To us it looks like a slow embrace. To the vine, its survival a steady ascent toward light. Watching a tendril wrap around a pole or branch is like seeing touch translated into growth proof that plants feel the world in almost tangible ways. A single oak tree can support thousands of other species. It's a bustling ecosystem unto itself. Branches shelter birds, squirrels, and insects. Bark harbors fungi, mosses, and lichens. Below-ground roots plug into vast fungal networks that nourish countless microbes. A mature oak can simultaneously support thousands of species, from tiny mites to large mammals. Each season brings a new layer of life blossoms for pollinators, acorns for animals, and fallen leaves that enrich the soil. Size and longevity make oaks foundation species, holding communities together. Standing beneath one, we're humbled by how many beings depend on it and how much history it has witnessed. Protecting an oak means protecting a web of life woven across centuries from wood and leaves. Some plants have translucent leaves to capture more light. Most leaves are opaque, but some species have evolved semi-transparent leaves, natural light windows that let sunlight penetrate deeper to photosynthetic tissues that would otherwise be shaded. The window plants, lithops of the desert, are a prime example. Their leaves lie buried with only the translucent tops exposed. Light passes through the window to the hidden photosynthetic tissues, keeping them safe from extreme heat and herbivores. Other species use similar tricks in dim forests, wringing every photon from scarce light. Translucent leaves blur the line between plant and crystal, turning sunlight into a resource that penetrates the body. A reminder that even leaf shape is an intricate survival strategy. City trees grow faster, but die younger. Urban environments create unusual conditions, higher CO2, warmer temperatures, and often abundant irrigation, making city trees grow faster than forest trees, produce more foliage, and reach maturity sooner. But the price of speed is a shortened lifespan due to pollution-compacted soils, urban heat islands, and limited space. A street tree may live only a few decades, while the same species in a forest can live for centuries. Short-lived as they are, they're still essential, cooling streets, filtering air, and sheltering wildlife. Each tree is a tireless ally, growing quickly to meet human needs, and its shortened lifespan is a reminder of the trade-offs of living in spaces shaped by us. Leaves can generate tiny electric fields as water moves within them. In every leaf, water rises from the roots through a microscopic network of vessels. As it moves, it creates weak charges that form a small electric field around the leaf, too faint for us to notice. But bees can. Bees sense a flower's charge and use it to tell which blossoms were recently visited. In that way, minute electrical activity becomes part of a communication language with pollinators. It's astonishing to think that the rustle of leaves is not only physics, but also electricity broadcasting invisible signals into the air. What seems like a simple green surface is actually packed with physics, guiding interactions between plants and insects. In every leaf, water, light, and electricity interweave, turning quiet growth into a hidden language of fields and charges. Some desert plants store water in swollen stems or roots. In the desert, survival depends on keeping water whenever it's available. Many species have evolved thickened stems, bases, or roots that act like reservoirs. Cacti store water in succulent tissues, swelling after rain and drawing it down during drought. Baobabs can swell their trunks to hold thousands of liters, becoming systems unto themselves. Below ground, some species develop massive tubers like hidden wells. These adaptations help them endure months, even years of aridity, staying green when everything else is withered. For people, that stored water can sometimes be life-saving when tapped in emergencies. Each swollen stem and root testifies to patience and preparation. In the desert, endurance is built on thrift, one drop at a time, stashed away in the vault of a living body. Rafflesia flowers can exceed 90 centimeters across, hidden in Southeast Asian forests. Rafflesia seems otherworldly. Its petals can surpass 90 centimeters, making it one of the largest flowers on Earth. A blotchy red surface like raw meat and a stench often compared to rot attract flies that pollinate it. Rafflesia has no leaves, stem, or roots of its own. It lives as a parasite within its host vine, drawing nutrients until it erupts as a gigantic bloom. Flowers are rare and short-lived, sometimes appearing only once after years. A single flower larger than a tabletop and smelling of decay serves a simple purpose: reproduction. It reminds us that plants can be as bizarre and dramatic as any creature, rewriting what we think a flower should be. Some mosses can survive total desiccation for many years. Certain species dry out almost completely and still live. In this crispy, dry state, metabolism nearly stops. Years later, after a single rain, they revive within hours, unfurling and greening again. This extraordinary toughness comes from protective proteins and sugars that shield cells against damage during drying. Thanks to it, mosses colonize harsh sites. Few others can tolerate cliff faces, arid deserts, even the surfaces of old buildings. They are pioneers, preparing the way for other life to follow. Watching a patch of brown, brittle moss spring emerald after rain is to witness a tiny resurrection, proof that life's resilience is often quiet and small, yet wondrous. Trees can sleep at night, slightly drooping their branches. Laser scans show many trees change posture. Overnight branches and leaves sag a little after dusk, then rise again with daylight. The movement is subtle, often only a few centimeters, but repeats regularly. This nocturnal sleep may help trees save energy or reset their internal water systems. It reflects the influence of circadian rhythms, internal clocks that govern many plant processes. Imagine an entire forest bowing gently as night falls, a glimpse of another layer of plant life, where as we rest, they do too, shifting softly in the dark. Then lifting their crowns to greet the sun, a gentle rhythm echoing the cycles of life throughout nature. Some plants thrive on volcanic ash and fresh lava fields. After eruptions, the landscape may look desolate with ash and hard rock, yet within a few years plants return. Pioneers like ferns, lichens, and hardy grasses take root in poor substrates, weather rock, and add organic matter, paving the way for others. In Hawaii, the ohia tree often colonizes new lava flows, first blooming bright red over black stone. Over time, volcanic soils become some of the world's most fertile, supporting rainforests and agriculture. Plants here remind us that destruction can be the seed of renewal. They turn fire and rock into gardens, desolation into life. Some plant species can change sex depending on conditions. In a few species, sex isn't fixed when resources are scarce. They may produce only pollen, avoiding the cost of making seeds. When conditions improve, the very same plant can switch back to producing fruits and seeds. Some alternate with the seasons, even changing multiple times in a lifetime. This flexibility boosts reproductive chances despite challenges, showing that in plants, sex isn't a rigid identity, but a survival strategy shaped by the environment where we expect fixed categories. Nature has written adaptability. Plants remind us that reproduction is not just endurance, but a smart response to a changing world. Some trees exude sap so toxic that it can blister skin. The manchineel tree in parts of the Caribbean and Central America looks inviting with glossy leaves and small apple-like fruits, but nearly every part is extremely poisonous. Its sap contains potent chemicals that can blister skin. Standing beneath it in rain is dangerous because water mixed with sap can cause painful reactions. Burning its wood releases smoke that harms lungs. As a result, the tree is often marked with warning signs or painted red to keep people away. Despite the danger, it stabilizes coastal soils and shelters wildlife, a reminder that beauty can hide peril. And in the plant world, defense strategies can be as dramatic as in animals. Grasslands once covered more than 1/3 of Earth's land area. Before large-scale agriculture and urbanization, immense prairies, savannas, and steppes stretched across continents, sustaining vast herds of grazers and countless other species. These ecosystems once carpeted over 1/30 of the terrestrial surface. Today, many grasslands have been plowed or fragmented, yet they remain crucial, storing enormous amounts of carbon in deep root systems, often more than forests of similar size, stabilizing soil, reducing erosion, and regulating water cycles. For myriad species, from bison to elephants to migratory birds, grasslands are vital. When we picture ecosystems, we often think of forests or oceans, but grasses have shaped the planet in their own quiet way. Abundance that doesn't tower high but spreads low and far, covering Earth like a living green skin. Some plants produce natural rubber or latex. Before synthetics, people relied on plants for rubber. The para rubber tree yields latex, a milky fluid that, once processed, becomes elastic and durable, essential for everything from tires to medical gloves. Other species like dandelion and guayule also produce latex, offering alternative rubber sources. For plants, latex is a defense, sealing wounds and deterring pests, while for us it became a material that shaped industrial civilization. When tissues are damaged, this sticky fluid plugs the injury and repels insects with bitterness or toxic compounds. For us, latex is a versatile resource. For the plant, it's a protective shield. The next time you snap a dandelion and see a drop of milky sap, you're witnessing the very defense mechanism that launched an entire industry. Rubber isn't just a factory product. It began as a simple survival trick, flowing through a tree's veins. Trees can trap ancient air bubbles in amber. Amber fossilized tree resin often preserves insects, leaves, and debris from prehistoric life. But inside that hardened resin are tiny bubbles sealed for millions of years, retaining ancient atmospheres and giving us clues to past climates. By analyzing gases in amber, researchers can estimate the composition of long-ago air, such as oxygen and carbon dioxide levels in the age of dinosaurs. It's remarkable that through sticky resin trees created time capsules holding the breath of ancient worlds. Every piece of amber is a record of Earth's atmosphere, sealed in golden light, whispering of forests long vanished. Some aquatic plants have completely water-repellent leaves. Water lily and lotus leaves have near miraculous surfaces. Droplets bead up, roll off, and leave them perfectly dry. The lotus effect arises from microscopic structures that prevent water from spreading. As droplets roll, they sweep away dust, keeping leaves clean. This adaptation helps aquatic plants reduce disease risk and ensures light reaches photosynthetic tissues below. The effect has inspired technology, water-repellent coatings, and self-cleaning materials. To us, it's an elegant, natural trick. To the plant, it's survival, a way to stay clean and dry while floating on water. Some flowers can catapult insects during pollination. Mountain rhododendrons, for example, have petals that act like tiny slingshots. When an insect lands, stored tension releases, flinging the visitor while dusting it with pollen. Other species use similar spring mechanisms to ensure pollen transfer by force and precision. To us, flowers look delicate, but beneath the petals lies hidden engineering storing energy for the exact right moment. Pollination, therefore, is both cooperation and surprise. Sudden movements helping reproduction avoid mere chance. There are fungi and plants that share light energy in symbiosis. While most plant-fungus partnerships focus on soil nutrients, scientists have found certain fungi living within plant tissues can harvest light and transfer some energy to the host. In return, the plant supplies sugars. This unusual relationship broadens photosynthetic capability, turning two very different organisms into partners in capturing energy. The finding is new, but it suggests that the boundary between plant and fungus isn't as hard as we thought. Sometimes the green world works, with hidden allies blending abilities to expand survival. Bamboo groves can reduce noise pollution like natural sound barriers. Dense stands of hollow culms don't just provide shade and greenery. Planted as thick hedges, they act as natural sound absorbers. The hollow tubes scatter and weaken sound waves, reducing noise from roads or cities. Hence, bamboo is useful in urban planning, sometimes used as a living noise fence. At the same time, it holds soil, prevents erosion, and provides habitat for countless species. Walking into a bamboo thicket is entering a quieter world. The air seems still, and outside sounds soften to a gentle hush, a reminder that plants shape the soundscape of our surroundings. Some seeds only germinate after passing through an animal's gut. For certain species, survival depends on this odd journey. Seeds are designed to be eaten, survive digestion, and be deposited elsewhere, often with a nutrient-rich fertilizer. Along the way, tough seed coats are abraded or softened by stomach acids, priming them to sprout a process called endozoochory that sends seeds far from the parent. Many fruits we love, from berries to cherries, evolved to entice animals for this purpose, food in exchange for transport. For us, fruit is nourishment. For the plant, it's a ticket to new ground. There were once forests near Antarctica. Today, Antarctica is an icy desert, but millions of years ago, it held lush forests. Fossils show giant trees, including relatives of modern conifers growing near the South Pole, enduring months of winter darkness and months of unending summer light. They may have grown dense like today's taiga, shaping ecosystems where dinosaurs once roamed. As the climate shifted and ice claimed the continent, Those forests vanished, leaving only petrified remnants, an echo of a once green land, reminding us that Earth's climate and ecosystems have never been static. Some plants produce fruit so toxic that it can kill large animals. Not every fruit is meant to be eaten. Some are formidable defenses wearing the guise of food. The strychnine tree bears seeds containing one of the most notorious poisons. Other species produce large, attractive fruits that are deadly to humans and mammals. Such toxic fruits ensure only the right species, often specialized toxin-tolerant dispersers, spread their seeds or simply prevent overbrowsing. Beauty can hide danger in the silent arms race between plants and animals. Powerful chemistry rivals claws and fangs. Leaves can adjust their angle to avoid overheating in summer. Many species actively tilt or droop leaves under intense sun to reduce direct exposure, lowering temperature and limiting water loss. Some, like prayer plants, move leaves daily, lifting them at night, lowering them by day. This subtle movement, hard to notice in real time, but obvious in time-lapse, shows that canopies aren't fixed ceilings, but shifting mosaics, each leaf seeking the perfect angle among light, heat, and water. Many plants sense gravity and always grow roots downward. Even in complete darkness, a seed knows up from down thanks to cells containing statoliths, tiny dense particles that settle in the direction of gravity. Roots respond by growing downward while shoots head upward. Gravitropism guides seedlings through soil along the correct axis. Without this finely tuned biological compass, roots might grow sideways or upward, making anchoring and water uptake difficult. Some trees keep a memory of lightning strikes in their rings. When lightning strikes intense heat and force damage tissues beneath the bark, leaving scars that alter growth. Years later, the injury is still visible in cross-sections. Dendrochronologists can identify such events centuries later, reconstructing a region's storm history. Some trees survive multiple strikes, carrying many scars in their wood. A reminder that every trunk is an archive of fire, drought, and lightning stored in quiet growth rings. Grass can give off a scent when cut as a stress signal. The fresh green smell we notice after mowing is a chemical cry. Grass releases volatile compounds, green leaf volatiles, that help defend itself, repel leaf eaters, and even attract the predators of those pests. At the same time, it warns neighbors to ramp up their defenses. To us, that smell evokes summer. To grass, it's an invisible alarm drifting through the air, proof that plants are constantly responding to their environment with signals we rarely notice. Some desert plants reflect sunlight with a silvery fuzz. In blistering heat, a few species coat their leaves with fine silver hairs that reflect light to reduce heat absorption and hold a layer of cooler air against the leaf surface. Desert sage and lavender wear this shimmering armor, looking pale and silvery under harsh sun, pleasing to our eyes, but a life-saving insulation for the plant. Survival sometimes lives in tiny details, from the angle of a leaf to a microscopic hair. Some plants produce edible roots that weigh hundreds of pounds. Yams, cassava, and many root crops store vast amounts of starch. In parts of Africa, giant yams weighing hundreds of pounds can feed a family for weeks. These swollen roots are the plant's pantry for drought and seasonal swings. For humans, they become staple foods that sustain millions. Digging up such a tuber is like uncovering a buried boulder, a hidden block of nutrition that proves life savings account strategy. Plants can secrete chemicals that suppress rivals. Not all plants cooperate. Some release compounds into the soil that slow or stop the growth of nearby plants. Allelopathy gives them a resource advantage. Black walnut is famous for juglone, which inhibits many species under its canopy. For these trees, it's a way to secure more water and nutrients. For their neighbors, it can be a silent killer. That chemistry shapes the look of forests and fields. What seems like peaceful coexistence is sometimes a battlefield of invisible toxins. Some flowers bloom only once in a human lifetime. Century plants. Agave americana save energy for decades in thick leaves, then shoot up a towering flower stalk over 6 meters tall, packed with blossoms. After that single performance, the plant dies, leaving seeds or offsets. Some bamboos also bloom only once after many decades or a century, sometimes synchronizing across entire regions. Witnessing such a bloom is rare, a glimpse of a botanical timetable, where patience and timing are woven on scales far beyond a human life. Mosses were among the first plants to conquer land. Hundreds of millions of years ago, continents were bare rock. The pioneers were mosses, and their kin no roots, no flowers, no seeds, spreading over moist surfaces, slowly breaking down rock and creating the first soils. By holding moisture and adding organic matter, mosses paved the way for larger plants and for entire ecosystems. Today, they still thrive where few others can, on cliffs, rooftops, and tundra. When you see a patch of moss flare emerald after rain, you're looking at descendants of the plants that made life on land possible, the story of Earth's great transition. Some plants change leaf shape as they grow. The phenomenon of heteroblasty makes leaves differ markedly with age. Eucalyptus begins with round opposite leaves, then shifts to long, narrow alternate leaves as it matures. Passion flower vines also change leaf forms as they climb, sometimes displaying multiple types on a single plant. These changes reflect shifting needs. Juveniles gather light near the ground, while adults optimize performance higher up. Changing leaf shapes can also frustrate herbivores that struggle to specialize on a single form. Seeing a plant wear many faces across its life is witnessing adaptation in action, evolution's quiet play unfolding in the canopy, as if plants rewrite their own identity as they mature, showing that even a leaf is never fixed. Some individual trees store more carbon than an entire small forest. Not all species have equal impact. Some, especially giant tropical trees, hold immense carbon in their trunks and branches. A single mature tree can lock up more carbon than a whole stand of smaller trees combined. In rainforests, these giants often live for centuries, each increment of growth sequestering CO2 for another century. Losing just one can have outsized effects both for carbon storage and for the ecosystem it anchors. Protecting them protects an entire web of life, from insects to birds to mammals, all tied to their presence. Standing in the shade of a towering trunk, you're not just looking at a tree, you're looking at a vast carbon reservoir, a living climate regulator. Their size isn't only awe-inspiring, it's crucial to Earth's balance. Plants can sense wind direction and adjust their growth. Plants are not passive to wind. Many species perceive wind's direction and force, then alter how they grow. In strong winds, stems grow shorter and thicker for stability. Some leaves pivot to reduce drag, others flutter to limit damage. These responses are guided by mechanosignals, tiny pressure and bending changes that trigger shifts in growth hormones. Over time, a plant takes on a shape suited to its wind regime, which is vital in open plains mountains and coasts battered by constant gusts. To us, rustling leaves seem random. To plants, wind is information data steering growth decisions at every stage. In those sways lies a subtle intelligence reshaping form to withstand the invisible force that presses on them daily. Some desert plants have roots deeper than a 10-story building. Where surface water is scarce, a few species dig astonishingly deep. Mesquite, for example, has roots recorded at over 45 meters taller than a 10-story building. These roots tap aquifers, letting the tree live where the surface is barren. That depth also anchors it against storms and erosion, making it almost impossible to uproot. Imagining roots plunging that far into darkness changes how we see deserts. A tree is truly not just what stands above ground, but a vast network below. These deep-rooted survivors show that endurance rests on hidden persistence, reaching for concealed resources to sustain life against all odds. In the Amazon, there are walking palms that slowly shift through the forest. In the Amazon rainforest, the so-called walking palm is famous for a curious claim: it steps by growing new roots toward light while letting old ones die back. Over the years, this can move the plant by a few centimeters to a few meters. While scientists still debate how much true movement occurs, the adaptation clearly helps the palm adjust to changing light under a dense canopy. The idea of a tree edging through the forest sounds like myth, but it holds a truth. Plants aren't as fixed as we think. Through slow adjustments, they seek opportunity, inching toward light where it appears. The walking palm reminds us that even rooted beings have ways to reach new horizons. Some seeds germinate only after fire bakes the soil. For certain species, fire isn't a threat, but a cue. In ecosystems like chaparral or pine forests, seeds lie dormant until exposed to heat or chemicals produced by wildfire. Flames crack hard seed coats or trigger compounds in smoke that spur germination, ensuring seedlings emerge into nutrient-rich ash just as competition has thinned. Far from pure destruction, fire becomes essential to renewal. Seeing sprouts push up from blackened earth is witnessing nature's resilient species that depend on catastrophe to begin again, turning disaster into opportunity and weaving fire into their life rhythm. Some plants can trap small animals for nutrients even though they aren't carnivorous. Carnivorous plants are famous for eating insects, but a few non-carnivorous species still hold small animals in ways that indirectly benefit them. Some bromeliads collect water in leaf tanks, creating tiny pools where insects, even small frogs, can drown. As they decompose, nutrients dissolve into the water and are absorbed by the plant. Certain sticky wildflowers snag insects on their surfaces, not to digest them directly, but to deter herbivory or to gain indirect nutrient benefits. They aren't true carnivores, but they blur the line, showing plants' opportunism. Survival strategies don't always fit tidy categories, and even gentle-seeming species can quietly profit from the fate of unwary visitors. There are trees whose branches fuse into living bridges. In the rainforests of India, people have learned to guide the aerial roots of fig trees to form living bridges. Over decades, the roots interweave and graft, creating structures sturdy enough for people to cross. Some of these living bridges stretch over 30 meters and last for centuries, strengthening with time. The trees themselves adapt, dropping new roots to reinforce the span. These bridges are both human-made and alive, a collaboration between people and trees. Crossing one is stepping onto a structure that is both architecture and organism, rooted in culture and biology. They are powerful reminders that plants aren't mere backdrop, but companions woven into human life in ways that feel almost mythic. Some plants can photosynthesize with their stems instead of leaves. Leaves are usually the main photosynthetic organs, but some species dispense with leaves entirely. In deserts, many reduce or shed leaves to save water, then turn their green stems into solar panels. Cacti are the classic example, using ribbed, thick stems to capture light while minimizing water loss. Some euphorbia species do the same. This adaptation lets them thrive where leaves would quickly wilt. To us, a cactus looks leafless and bare, but its whole body is functioning as a giant photosynthetic organ. An elegant solution swap fragile leaves for a robust stem, so the entire plant operates like one big leaf. The shift shows plants redesigning themselves to endure extremes, finding new ways to turn sunlight into life. Bamboo flowering is so rare that it may happen only once in more than a century. Bamboo is famous for rapid growth, but its flowering is among nature's rarest events. Many species bloom just once every 60, 80, or even 120 years. When they finally do, entire populations often flower in sync, regardless of location, a mysterious synchronization science still doesn't fully understand. Afterward, most bamboo dies, leaving seeds for the next generation. This mass die-off can reshape ecosystems, creating sudden food pulses for wildlife, but also lean periods that follow. For communities that rely on bamboo, these cycles can be disruptive. The phenomenon feels almost legendary. Plants that wait decades or centuries for a single bloom to witness it is rare, a reminder that some natural rhythms stretch far beyond a human lifetime, written in life cycles measured by centuries. Some plants can grow without soil, directly in air or water. Though we often think soil is essential, many species do just fine without it. Epiphytes like orchids and tillandsias, air plants, grow on tree trunks, drawing water and nutrients from the air and rain. In aquatic settings, species like water hyacinth float freely, taking everything they need directly from the water. Hydroponic farming borrows from these natural strategies, letting people cultivate plants without soil using nutrient solutions. Such species show that while soil is useful, it isn't strictly necessary. They remind us that life adapts to every niche, clinging to bark, drifting on ponds, or thriving in systems we design. Seeing a hanging orchid or an air plant flourish without roots in soil is witnessing the plant kingdom's flexibility. Survival sometimes means bending the rules we thought were universal. Flowers can create ultraviolet patterns invisible to humans. To us, many blossoms seem like simple patches of color, but to pollinators like bees, they carry hidden patterns painted in ultraviolet nectar, guides pointing straight to the center where nectar and pollen wait. They work like runways, guiding insects in for a precise landing. Each species has its own UV design, visible only with special filters. What looks plain white or pale yellow to us can blaze with contrast in a bee's view. This hidden beauty shows that flowers are tailored not for human eyes, but for pollinators' senses. The world around us, therefore, carries layers of color and signal beyond human perception. Whole fields more vivid than we imagine. Living landscapes mapped with invisible guides for tiny visitors from the sky. Some plants can change the soil's acidity where they grow. Plants don't just adapt to soil. Sometimes they remodel it by secreting chemicals from their roots that alter the surrounding pH, making it more acidic or more alkaline. This ability shapes which species can grow nearby, giving the host a competitive edge. For example, pines and oaks drop acidic litter that lowers soil pH, favoring organisms adapted to those conditions. Other species raise pH to improve nutrient availability. These changes ripple through entire ecosystems, affecting fungi, microbes, and even animals. The ground beneath our feet isn't static. It's constantly being reshaped by the plants living in it. Every forest floor and grassland carries the vegetation's chemical fingerprint, a living record of how plants engineer their environment to suit their needs. Some trees pump water higher than skyscrapers. One of plant biology's great marvels is how tall trees move water from roots to the highest leaves. In species like coast redwoods, water must ascend over 90 meters taller than many buildings. The mechanism relies on cohesion among water molecules combined with the pull created by evaporation at the leaves, forming a continuous stream from root to crown, climbing against gravity without pumps or muscles. This feat is so extreme that scientists still study the limits of how high water can rise. Yet forests prove it happens daily, quietly and flawlessly. Standing beneath a sky-piercing canopy and knowing every leaf above is drinking from the ground below is to marvel at a living system more efficient than many machines we build. The Amazon's rising waters flood forests where fish pollinate trees. Each year, seasonal rains swell the river, flooding vast forests. Instead of destruction, this cycle sparks astonishing adaptations. Some trees flower and fruit as waters rise, relying on fish to disperse seeds. Fish eat fallen fruits, carry the seeds, and plant them elsewhere. In this way, fish act as pollinators and dispersers in a system where water and forest merge. Flooded forests turn surreal trunks submerged while animals swim among the trees, a vivid reminder that plants are woven into networks with animals, rivers, and climate. In the Amazon, even fish help trees, proof that cooperation can emerge in the most unexpected ways. Some plants use sticky hairs to trap and drown insects. Not every plant that traps insects is truly carnivorous. Some use sticky hairs on leaves or stems to snare insects that land on them. Once caught, the insects may die and decompose, with nutrients seeping into the soil and indirectly feeding the plant. In other cases, the stickiness simply discourages herbivores because it's unpleasant. In a few species, like wild tobacco, sticky hairs hold onto would-be leaf eaters, turning their corpses into a protective shield. These strategies blur the line between passive defense and active foraging, showing plants deploy countless survival variations that mix stickiness, chemistry, and chance. A hair that looks delicate on a leaf can be a deadly trap, not to feed the plant directly, but to tip the balance against the insect world. Plants can produce toxins potent enough to become medicines. Many of the world's most powerful drugs began as plant poisons. Foxglove makes compounds that in controlled doses can treat heart disease. Willow bark contains salicin, the precursor to aspirin. The rosy periwinkle gave rise to life-saving chemotherapy drugs. These chemicals evolved as defenses, bitterness, or toxicity to deter herbivores. But humans learned to harness them, turning poison into remedy. That duality, danger intertwined with healing, reveals the complexity of plant chemistry. Every forest and meadow hides medicinal potential waiting to be found. The next leaf or blossom might hold a life-saving molecule. For plants, it's merely defense. For us, it's possibility. Inside each toxin is a hidden gift, reminding us the line between harm and cure is thinner than we think. Some algae blur the boundary between plant and animal life. Algae are often grouped with plants, but certain species defy neat categories. Some both photosynthesize like plants and move or hunt like animals. Dinoflagellates, for instance, can make their own food and capture prey. Other algae form symbioses with animals living inside corals or sea slugs to share energy. These organisms highlight the fuzzy edges between plant and animal evolution has trialed many ways to capture energy, and algae sight at the crossroads. To us, they seem simple, yet they represent some of Earth's oldest, most flexible forms of life. Peer into a drop of pond water and you'll see this hidden versatility, tiny beings reminding us that labels are human inventions while life refuses tidy boxes. Trees can live for thousands of years, older than civilizations. Some trees are so ancient they predate many cultures. Bristlecone pines in California have lived nearly 5,000 years older than the Egyptian pyramids. Olives, yews, and sequoias also reach extraordinary ages, standing witness to millennia of change. Their endurance comes from slow growth, dense wood, and the ability to wall off damaged tissues. These trees aren't just organisms, they're living archives recording climate shifts, droughts, and fires in their rings. Standing beside one is brushing against deep time, feeling the presence of a life that outlasted empires and languages. They remind us that in the plant kingdom, patience can be the ultimate strategy. Humans measure history in centuries, while trees quietly count in millennia, standing still yet stretching across time. Trees can live for thousands of years, older than entire civilizations. Some are so ancient that they far exceed human history as we know it. Bristlecone pines in California, for example, have lived nearly 5 millennia. These hardy survivors sprouted long before the pyramids were raised, enduring storms, drought, and centuries of change. Their wood grows slowly and tightly, resisting rot, while damaged tissues can be isolated to protect the core. Each annual ring is a tally of years, giving science a climate timeline spanning thousands of seasons. Standing by such a trunk, you feel time's weight graze your skin. They remind us that as civilizations rise and fall, nature continues in silence, rooted in patience. Trees aren't merely witnesses to history, they are living history, breathing in the present, while holding stories that reach deep into the past. Some plants can smell nearby pollinators and respond. Plants don't have noses, but they can sense scent molecules in the air. Certain species detect chemicals released by pollinators and respond almost instantly. For example, some flowers increase nectar output or boost their own fragrance when they catch a whiff of bee pheromones nearby. Others adjust the timing of bloom to be most inviting at the right moment. This sensitivity is like a botanical sense of smell, letting plants anticipate and sync with the animals they rely on. To us, a flower smelling a bee sounds strange, but it reflects the astonishing sophistication of plant senses. They live in a constant dialogue with their environment, reading cues far beyond our abilities. As we stroll past a garden we may not notice, but the plants may already have answered their visitors, subtle as breath drifting on the air. Some vines strangle entire trees to reach the light. Not all climbers are gentle. A few, like the strangler fig, begin life as a tiny seed dropped onto another tree's branch by a bird. From there, the seedling sends roots downward, wrapping tightly around the host. Over decades, the roots thicken, constricting the host until it dies. In the end, the fig stands on its own, supported by its lattice of roots, having used the host as scaffolding. This strategy lets the vine reach light in dense forests, avoiding the struggle that begins on the dim forest floor. To see a strangler fig is to see beauty and brutality interwoven, a living reminder that plants also compete fiercely to survive. Lacking teeth or claws, they conquer with patience and pressure, reshaping the forest tree by tree. The oldest known tree is nearly 5,000 years old. High in California's mountains stands an individual called Methuselah, a bristlecone pine estimated at almost 5,000 years old. It sprouted long before writing agriculture or the rise of great civilizations. Gnarled by time, it survives in harsh conditions where few plants endure cold winds. Thin soils and extreme weather haven't killed it. Instead, they've preserved it, slowing growth to a crawl. Each year adds a hair-thin ring, building a body dense and resilient. Methuselah stands among Earth's oldest living beings, older than empires, older than myth. Its existence humbles us, reminding us that life can stretch across time scales far beyond human imagination. When we count decades, Methuselah counts millennia, standing silent as ages pass beneath its patient branches. Some species can survive in scalding hot springs, in the harshest environments where water bubbles and steams near boiling a few life forms persist. Algae and mosses have been found in geothermal pools, thriving where few organisms dare. Their proteins and cell structures are adapted to withstand heat that destroys ordinary plants, allowing photosynthesis in shimmering, steam-filled worlds. These hardy pioneers are studied to understand life's capabilities, from biotechnology to the search for life beyond Earth. If life survives boiling water here, perhaps it can endure similar extremes on other worlds. Seeing green filaments thread through searing pools reveals how boundless life's will can be. Even where conditions seem utterly hostile, plants find ways to persist, turning heat into habitat. Leaves can trap air bubbles to help aquatic plants float. For underwater species, buoyancy matters as much as anchoring. Many aquatic plants evolved leaves with structures that trap air bubbles, tiny life vests that lift them near the surface to catch light. Lotus leaves, for example, repel water and encourage bubble formation, keeping the leaf afloat and dry. Other aquatic plants have spongy tissues riddled with air spaces that buoy whole stems. The result is a delicate balance between sinking and floating, guided by hidden pockets of air. To us, a lily pad drifting on a pond is a tranquil scene. Inside the leaf, though, is engineering as precise as any boat, a living raft holding sunlight steady on the water. Each floating leaf is a reminder of nature's ingenuity, rising with nothing more than bubbles and breath. Some plants defend themselves with microscopic crystals hidden in their tissues. Behind the softness of many leaves lies a secret shield. Certain species form minute calcium oxalate crystals shaped like tiny needles. When an animal bites the leaf, these crystals spear the soft tissues in the mouth, causing irritation, swelling, and even burning pain. The effect is immediate and memorable, deterring further feeding. Taro rhubarb and Dieffenbachia, also called dumb cane, are among those that use this strategy. For humans, they can be hazardous if eaten raw. In the wild, they're like invisible armor until disturbed. The idea that a leaf can hide a forest of knives is astonishing. Plants may look fragile, but their chemistry and structures often create defenses more effective than thorns or bark. Every bite is a gamble, a reminder to herbivores that even the gentlest greenery can strike back in unseen ways. Flowers sometimes bloom in unison across vast areas. In some species, flowering isn't an individual choice, but a coordinated event. Certain bamboos, for instance, flower simultaneously across regions separated by hundreds of miles, synchronization driven by mysterious internal clocks that can span decades. Once the bloom ends, plants set seed and die, resetting the cycle. The result can be a sudden glut of food for wildlife, followed by scarcity when the plants perish. Other species, like some desert wildflowers, also bloom en masse after rare rains, rolling out spectacular waves of color across the landscape. These events remind us that plants run on rhythms. We rarely sense tempos not measured in hours or seasons, but in decades and centuries. When the moment arrives, the result is breathtaking. A land transformed, as if the plants chose to sing in chorus, releasing their beauty all at once. Some plants remember touch for minutes at a time. Experiments with the sensitive plant Mimosa pudica show. It can remember being touched when repeatedly stimulated. Its leaves stop folding, as if the plant has learned that this particular stimulus is harmless. Strikingly, this memory can persist for minutes or even hours before fading. It isn't memory in the animal sense, but a form of physiological information storage. The plant modulates its response based on past experience, saving energy by ignoring irrelevant signals. This suggests plants don't merely react blindly, they process information in subtle ways. The notion of a leaf retaining the trace of a touch is stunning. It blurs the line between sensation and thought, hinting that intelligence can take many forms, sometimes green and quiet, like a leaf holding the shadow of a moment long after it has passed. Some plants can regrow entirely from a fallen branch. For certain species, a broken limb isn't the end. If a branch falls to the ground under the right conditions, it can root and become a new tree. Willows, poplars, and figs are famous for this regenerative power. In some tropical regions, whole groves arise from such rooted branches, all genetically identical to the parent. This ability ensures survival after storms or damage, turning accidents into opportunities. To us, a fallen branch is debris. To the plant, it's simply another chance at life, another reach for the sky. This resilience shows that plants refuse to be defined by fragility. Even when fractured, they carry the potential to rise again, softening the boundary between endings and beginnings. Plants remind us that life on Earth is both fragile and wondrous. From the smallest moss to ancient giants, plants embody resilience, creativity, and patience. They shape the air we breathe, the food we eat, and the landscapes we inhabit. Yet they're vulnerable to drought, fire, disease, and human impact. Their survival is a delicate balance achieved through sophisticated strategies, chemical defenses, hidden senses, and astonishing adaptations. In their silence, they're easy to overlook, but when we pause, we see their richness. Forests that make rain seeds waiting for centuries, roots deeper than buildings. Flowers that sense and respond to their world plants remind us that life isn't only fierce, it's endlessly inventive, weaving survival into every leaf and root. And so we reach the end of our journey through the hidden lives of plants. From whispering root networks underground to trees older than civilization, we see they were never truly silent. They are ecosystem architects, chemists of survival, and timekeepers of the earth. Every leaf, stem, blossom, and seed carries stories of patience, endurance, and quiet ingenuity. As you drift towards sleep, imagine yourself in a nighttime forest. Cool air canopies above, gently shifting with the breeze. Somewhere a flower opens in the dark. A tree lowers its branches to rest until dawn. Beneath the soil, roots slowly thread through the night, searching, sensing alive. Thank you for staying with Easy Sleep Science Channel to explore the secret world of plants. If you enjoyed this journey, please like the video, subscribe, and come back for our next wondrous science walks. For now, let your mind settle, your body soften, and your breath slow. The green world holds you in its quiet. Sleep well and dream beneath the leaves.